Assalamu alaikum, dear students. This time I want to deliver one more lecture on this differential equations. It is in fact the ordinary differential equations. Before this we did up to fifth lecture, where in fifth lecture we were doing the questions which were reducible to variable separable form. We did some questions. Let us have some more questions on this. Suppose I take a question here. This is the application. Suppose you have to solve the differential equation, ordinary differential equation. It is cos of x plus y plus dy by dx is equal to, let it be dy by dx equal to cos of x plus y plus sine of x plus y minus 1. This is the differential equation you want to solve. You see here again, in previous lecture number 5 we were having some questions where x and y was mixed up, where we could not separate functions of x with dx and functions of y with dy directly. What we did there, we make some suitable substitution which helped us to write the differential equation in such a way that it is going to variable separable form. This is also one more question we want to share with you, how we solve this equation by previous method. Let me put here z is equal to x plus y. I made the substitution z is equal to x plus y. Similarly, in similar way that we did in lecture number 5, that is the differential equations which are not directly in a position to write the variable separable form, but under certain conditions we may make a substitution where the differential equation gets converted into variable separable form. This is one of the problem on that. This will be your dz by dx, differentiating with respect to x both sides. It is 1 plus dy by dx. Well, this gives me dy by dx is what? This is your dz by dx minus 1. Dz by dx minus 1. So equation number 1 now is, equation number 1 implies it is dz by dx minus 1 is cos z plus sin z minus 1. It is dz by dx 1 plus, this gives dy by dx is dz by dx minus 1 into this. So this implies dz by dx will be cos z plus sin z. Okay, this one simplification gives me dz by sin z plus cos z is equal to dx. What is this now? Variables got separated. You have separated the variables here. When you have separated the variables, that means you can integrate this now. It is integral of dz by sin z plus cos z is equal to integral of 1 dx plus c. So this is your integral of dz by sin z plus cos z is x plus c. This is number second equation. You see, I want to just review here how you integrate. In previous classes you have the integral of like this, dx by a cos x plus b sin x. It takes the same form, sin x plus cos x. You actually put a is equal to r cos theta, b is equal to r sin theta. Then you proceed. This integral dx by a cos x plus b sin x, you can reduce it to the integral of sec x dx, sec z dz, or you can this reduce it to the integral of cosec z dz. In both cases, it is up to you whether you put a is equal to r. If you put a is equal to r sine theta, b is equal to r cos theta, then it will be 1 by this. It will become sine formula, sine of a plus b. If you put this as a as r cos theta, b as r sine theta, this will be cos formula, cos of a plus b, 1 by cos, the formula that becomes sec. So you can reduce this integral into sec or cosec. Therefore, the answer may vary if we reduce. It is up to you. There is no hard and fast rule. But the method is, whenever you come across an integrand like this, make the substitution this, it will get reduced. Similar, we are getting an integral here. You see how I solve this integral now. You see how I do it. My integral is now this. I will write it integral of dx by 1 cos x plus 1, sorry, it is z, 1 sin z, it is dz here, 1 sin z is equal to x plus c. You have this one, it is your a, this is your b. It is as per your choice, or there is one more. Since the coefficients of cos and sine are same, I can put here root 2 divided by 1 by root 2, because the angle which has the same this value, this sine 45 cos 45. This way you can also do. Let us put 1 is equal to r cos theta and another one is equal to r sine theta. This gives me, by squaring and adding, r square is equal to 2. This gives r is root 2. By dividing this, that is r sine theta by r cos theta. This is what you do in your previous class, in 12th class in school. This your integration. Tan theta is, it is 1. That means theta is pi by 4. You have got this value. This is what you, how you are doing in lower classes. I am just reviewing your work, what you did there. Okay. This is now, I can write this integral this way. It is integral of dz like this, r cos theta cos z plus r sin theta sin z is x plus c. This is your 1 by r integral of dz by cos z cos theta plus sin z sin theta is x plus c. This implies 1 by root 2, your r is root 2, integral of dz, this becomes cos a cos b plus sin a sin b, it is cos of z minus theta is equal to x plus c. This is your 1 by root 2, this is your integral of secant z minus theta dz is x plus c. Okay. Now you have integral of sec theta d theta. You know what is this? Yeah, this is log of sec theta plus tan theta. Or you can write it is also log of tan x by 2 plus pi by 4. In that way also you can do. Now accordingly, this is 1 by root 2. Using that, it is log of sec. It is sec z minus theta plus tan z minus theta is equal to x plus c. This is 1 by root 2. This will be log sec. What is your z? You give the value to z. Previously your substitution, it is x plus y minus, what is theta there? Pi by 4. Then plus tan x plus y minus pi by 4 is equal to x plus c. This is the solution of this differential equation. Or if you don't use this formula, you can use this log of tan x by 2 plus pi by 4. Your x is your z minus theta by 2. You can do it this way also or this way also. This is how we tackle the problems where we cannot, in certain cases, write the functions of x with dx, functions of y dy, but it seems it happens that by the suitable substitution we can reduce the differential equation in such a way that we can separate the variables, but it is not a necessary and sufficient condition. You cannot do it always where the differential equation is not such that we cannot separate the variables. We will go for the substitution, not directly, not always. But when you find that x and y are mixed up together by putting x plus y is equal to something, x minus y is equal to something, it reduces to a single variable. That is, one variable gets reduced there. It involves x plus y, one variable gets reduced. Instead of one variable we have z. We can do it in that way. But in certain cases when it is not possible, we have another methods. One is the homogeneous. Now we shall deal with very important method of solving the ordinary differential equation of first order and first degree, that is known as homogeneous differential equation. We shall deal with it. We shall take it now, and we will be now doing those differential equations. Well, we have now homogeneous differential equations. Homogeneous differential equations, but these are of first order and first degree. First order and first degree, because later on when we go in differential equations ahead of this, after that we have to Bernoulli's, then we have exact, then we have soluble for P. In certain cases we will have a differential equation which is not of first nth degree, that will be a linear of nth order, nth degree. So it is a first order and first degree. Here we are doing the homogeneous differential equation of first order and first degree. After that you will again come across homogeneous differential equation. I will tell you there which is of nth order. Order will be nth, but it will be a homogeneous. In any way, this is first order and first degree. Before defining what is a homogeneous differential equation and what is the method of solution, I would like to recapitulate your definition of homogeneous function in two variables or three variables. You did it in your differential calculus, where you do the homogeneous functions. Then you have a very important theorem on homogeneous function. It is Euler's on partial differential equations. You did this homogeneous differential equations. I will differential this homogeneous functions. I will just define what we mean by definition of homogeneous function. What do we mean by homogeneous function? Say two variables. We can have homogeneous of more than two variables. We shall take here homogeneous function of two variables. We can take first definition. A function u is equal to f of xy. It is function of two variables, x and y, is said to be homogeneous of degree n if f of tx ty we can write t raised to power n f of xy. This is the first definition. What is here t? Where t is independent of x and y, and t is any real number. It is independent of what? X and y, but t is a real number. This is one definition of homogeneous. You can define in this way also. Second definition, sometimes we use this definition, or u is equal to f of xy is said to be homogeneous of degree n. If you can write this u, if u is equal to f of x, you can write this in the form of x raised power n f of y by x. Here this is what the power of n you get out. This is known as the degree of this. N is the degree. Or if you can write, or f of xy you can put in the form y raised power n f of x by y. It is x raised power n f of y by x. This is y raised power n. In this case also we say it is a homogeneous. This is the definition. We will be using this definition of homogeneous in determining the homogeneous differential equation of first order and first degree. Once we come to know it is a homogeneous differential equation, then we can apply the method of solution which is applicable for homogeneous differential equations. At this time I am not defining the homogeneous differential equation. I am just defining what we mean by homogeneous function of two variables or three variables. Okay, let me see how we apply this. You did it in your differential calculus. There is a separate chapter there where you do the homogeneous differential equations, and there are some terms, Euler's theorem, so on and so forth. Let us have let me take an example here. You see, I take some example. Let us consider f of xy is equal to ax square 2hxy plus by square. By just a glance at this this equation, homogeneous equation of degree, this variable, two variable, it is homogeneous because here degree is 2, x has degree 1, y has degree 1, 1 plus 1 is 2. In that way you can go. Y is, if you apply the definition, you see, if we go this, if we tackle this along the definition, I have f of xy is equal to ax square plus 2hxy plus by square. If you replace x by tx, t is some real number but is independent of x and y. Y I replace by ty. You see what happens. Differential equation comes back. Sorry, this equation comes back. Homogeneous equation will come back with t power of t. You see, this is a. This is tx square plus 2h. This is your tx. This is your ty. I am replacing y by ty plus b ty square. What is this? You see, it is t square out. This is ax square plus 2hxy plus by square. What you get? You get f of tx ty is t square. This is again f of xy. So you apply the definition here. The definition we did. Now you get the value of power here t2. So this implies f of xy is homogeneous of degree second. Now you look, if you apply second this definition, I have also given one more definition. Second definition, you have again f of xy, same question I take, ax square plus 2hxy plus by square. I write it f of xy is, take x square common, I can write it a plus 2h xy by x square plus by square by x square, because when you take any term common, actually we are dividing by that. This is f of xy is x square. You can write it a plus 2h y by x plus b y by x square. That means interior of this function we could write each and every term in the form of y by x. You see now we have f of xy is equal to x square. This you can write a times, this is also, it also involves the term y by x. What is that? Y by x raised to power 0. It is 2h y by x raised to power 1 plus b y by x square. So what is this by definition? It is also homogeneous. Note that this no term should contain here x term, y term. Each and every term should contain the powers of y by x only. Here you have the power of y by x naught. Here you have the power of y by x1. Here you have the power of y by x square. No x or y with this, no x or y with this, no x or, but here outside we have the power x2. So it is a homogeneous. So this implies what? F of xy is homogeneous. Homogeneous of degree second. So I have applied the two definitions to the same question. I have applied two definitions to the same question. So I have proved how it is how we test the homogeneity of a function. This is the test of homogeneity of a function. Now we shall define the homogeneous differential equation. Then we will give you the method of solution. Okay, this is homogeneous. Now consider, this is the definition of homogeneous differential equation. First order and first degree I rule. You consider, if you have a differential equation, consider the differential equation dy by dx, it is some function of f of xy. Here you have some function of g of xy. First of all, you have to see, is numerator homogeneous? F of xy, if number one, f of xy is homogeneous. You have now seen how we test homogeneity. Number second, g of xy. What is g of xy? Numerator is this. G of xy is what? Denominator. G of xy is also homogeneous. But in some cases, if it is a homogeneous of degree third, but this is a homogeneous of degree 2, we say our differential equation is not homogeneous. So when it is homogeneous? It is homogeneous when it satisfies third condition. Degree of f of xy must be equal to degree of g of xy when both are homogeneous. What is the degree of numerator? That must be the degree of denominator. Then we say it is a homogeneous. For example, you have examples. Suppose we have examples here. I can quote example. Suppose I come across somewhere dy by dx is, say it is x square plus y square by xy, simple. This is the differential equation. Now look at the numerator. Degree 2 x square, degree 2 here also. So we say numerator is homogeneous. Now come to the denominator. Here degree 1, this is considered to be 2. You have seen there. This is 2. So this is homogeneous of degree 2. This is also homogeneous of degree 2. So we say this differential equation is now homogeneous. Okay. Suppose you come across a differential equation like this. you have differential equation. dy by dx is under root of x square plus y square by x, simple. You look here, x square, you say it is degree 2. Second term, y square, you say it is degree 2. So we say the function under radical. Function under radical is a homogeneous of degree 2, but it is under radical. So radical has its own power but 1. So this is homogeneous of what? Numerator. It is a homogeneous of degree first. And this is also degree first. It is single term, degree first. This is also degree first. So we say dy by dx is homogeneous. Okay. You may have somewhere, suppose you have dy by dx. dy by dx is x cube plus y cube, and denominator is xy square plus yx square. This is dy by dx x cube plus y cube, and denominator is xy square plus yx square. What about numerator? Degree 3, degree 3. So numerator becomes homogeneous. Every term is degree 3. Now come to the denominator. X square, xy square, degree 3. Y degree 1, x square degree 2, so it is degree 3, degree 3, degree 3, so it is also homogeneous. Numerator homogeneous, denominator homogeneous, but of same degree. So our differential equation is a homogeneous. This is how we look this differential equation when it is a homogeneous. There is no need of going to that test which I applied for ax square plus 2hxy plus by square is equal to 0. F of xy is equal to that. But you have to just look at the differential equation and see is it homogeneous, then apply the method of solution. What method we apply for solving the homogeneous differential equation? Now I will give you the this method of solution for solving the homogeneous differential equations of first order and first degree. I will give you the method, then we will take some applications. This is now method of solution. How we solve of, or you can write method of solution for homogeneous differential equation of first order and first degree. This is the method of solution. Suppose dy by dx is a differential equation which is numerator is some function of xy, it is some function of xy, but this is homogeneous. Suppose it is homogeneous. First we have to see is it a homogeneous. How we see that? I have told you how we see that it is a homogeneous. Then method of solution is, this is the first step. We put y is equal to vx. V is not constant, it is also variable. V is considered to be variable. Y is equal to vx. We find out here dy by dx. Differentiation of x is 1, it is 1 into v plus x. V is also a function of x and y. We write it dv by dx because it is a variable. V is not a constant. Therefore you get dy by dx is equal to v plus x dv by dx. Now what we do is we use this value, use in first. When we use this value in first, you will see that differential equation is converted into variable separable method. Differential equation first can be solved by variable separable method, and it will involve two variables now, v and x. You don't find here y, you will replace then y by vx, and using dy by dx is equal to this. You have to use two things in first. You have to replace y by vx, you have to replace dy by dx by v plus x in this, and this differential equation will be converted into a differential equation where you can apply variables separable method. In certain cases if you get differential equation like if you have differential equation dx by dy is equal to, say it is f of xy f1 xy by f2 xy, if it is homogeneous, but it is not dy by dx, it is a dx by dy. Here you will make the substitution, put suitable substitution, you will put x is equal to vy, you will get dx by dy. What it is? It is v plus y dv by dy. And in that way, this you have to replace there x by vy, it will be involve y and dv, y and v, then by variable separable you can solve it. This is the method of solution, very simple. First we have to see, is the differential equation homogeneous, first order and first degree, and if it is, then we take help of this y is equal to vx, if it is dy by dx here. If the differential equations itself, every term is in the form of y by x, you will see some differential equations where each term is in the form of y by x, dy by dx is equal to y by x, you put there y is equal to vx. In some cases you find a differential equation dx by dy where right side is such that every term is in the form of x by y, put there x is equal to vy, and so on. Let me have the application on this. Okay dear, now we shall take application part. Applications. As a first application, I will write first, solve the differential equation, solve x plus y dy by dx plus x minus y equal to 0. Solve this differential equation. It is x plus y dy by dx plus x minus y is equal to 0. Solve this. You see how we solve it. You can write this differential equation as x plus y dy by dx is y minus x. This is dy by dx is y minus x by x plus y. You see in this differential equation, no need of writing, let us name this here 1. This differential equation is such we cannot separate the variables here. We have solved it for dy by dx. On right side we see, let us look at the numerator. Numerator, first function is y degree 1, second term is x degree 1. So we say it is a homogeneous part, numerator of degree 1. Now what is denominator? X power 1, y power 1. This is also homogeneous. Why is homogeneous? Every term is of same order, that is 1, 1, 1, 1, 1. Now degree of this is degree of this. It is a homogeneous differential equation of degree first. It is homogeneous differential equation. Homogeneous differential equation of first degree, degree 1. So what we do is we put y is equal to vx. This is dy by dx is v plus x dv by dx. Using in first, what you get, it is v plus x dv by dx is equal to y is your vx minus x, it is x plus vx. Now look at this differential equation. You don't have y now, you have only v and x. So we have to try it separable for this v terms with dv and x terms with dx. We can write this differential equation further as it is v plus x dv by dx is equal to, it is v minus 1 by 1 plus v. You can write this x dv by dx is, it is v minus 1 by v plus 1 minus v, which gives x dv by dx is v minus 1 minus v square minus v by v plus 1. This is x dv by dx is equal to, this positive v negative v will not survive, minus times v square plus 1 by v plus 1. Now we are in a position to separate v terms with dv. How? This is v plus 1 by v square plus 1. Here you have dv, it is minus here 1 by x dx. So you say variable is separated. Variables got separated. Do you follow me? This is how it was a homogeneous. We put y is equal to vx, and then by suitable substitution, this involves only v and x. We could separate v terms with dv and x terms with dx, so it is variable separable. Let us see how we solve it. This is variables are separated, so integral of v plus 1 by v square plus 1 dv minus integral of 1 by x dx, add constant of integration. We can separate here this way, integral of v by v square plus 1 plus integral of 1 by v square plus 1, it is dv here, it is dv, it is your minus log x plus c. Okay, now you see I have separated this. This is v first degree, it is second degree. I have to, whenever you numerator is the first degree, denominator is the second degree, we try to write numerator derivative of denominator. We can do it because derivative of v square plus 1 is 2v. So we can write here 2v. For that I have to divide by 2 and multiply by 2, so that it is fx by fx. So this I can write here 1 by 2. I write here 2v by v square plus 1 dv, and you know what is integral of 1 by x square plus 1 dx. It is tan inverse, so it is tan inverse v. If you have any difficulty, again I have already told you that integration is the language of differential equations. Remember this, integration is purely the language of differential equations. Whenever you solve the differential equations, you should have the integral concept strong. If you have any difficulty, again integration, then you have some lectures on my YouTube channel. These are the basics of integration. I have given there basics of integration. You should go again through those lectures so that you can make your integration strong. Okay, well, what I am doing here, why I multiply by 2? Because I am writing numerator as the derivative of denominator. When I differentiate v square plus 1, it is 2v. So this is f dash, this is f. So it is also the formula. Whenever we can write the integrand as f dash by fx, it is log of the denominator. So you can write this now. It is 1 by 2 log of v square plus 1. Then it is plus tan inverse v is equal to minus log x plus c. In any way, what you do is now give the value to v. You have put y is equal to vx there. Your substitution was what? Y is equal to vx. Now your v will be what? Y by x. Replace v by y by x. so that you will get 1 by 2 log of, it is now y square by x square plus 1 plus tan inverse y by x is minus log x plus c. This gives 1 by 2 log of x square plus y square by x square, then plus tan inverse y by x is minus log x plus c. If here it is not visible, this setup, I will go again top step. Well, here you can write it is 1 by 2 log of x square plus y square by x square, then plus tan inverse y by x is equal to minus log x plus c. Here I can apply the log of m by n formula if I want to further simplify this. Log of x square plus y square minus log of x square, then it is plus tan inverse y by x is minus log x plus c. Well, this is 1 by 2 log of x square plus y square. This is minus 1 by 2. You can take 2 down. It is 2 into log of x, log of m raised power n, plus tan inverse y by x is minus log x plus c. You can write it 1 by 2 log of x square plus y square. This is minus log x plus tan inverse y by x is minus log x plus c. This minus log x goes. So you have the solution of this. Solution is 1 by 2 log of x square plus y square plus tan inverse y by x is c. This is the solution of your given differential equation. When it was a homogeneous, the differential equation was not in a position that we could separate the variables. When it is a homogeneous, we could put y is equal to vx and we could separate it as variables. Now we have some more applications. Suppose I take one more application here. Application number 2, solve differential equation. It is x square y dx, x square y dx minus x cube plus y cube dy is equal to 0. This is the differential equation, x square y dx minus x cube plus y cube dy is 0. You see, I rewrite this differential equation this way. This I can write x cube plus y cube dy is x square y dx. So that you can write dy by dx will be, your dy by dx is x square y by x cube plus y cube. This is x square y dx minus this. Okay, let us name this first. You look at numerator, degree 1, then multiplying factor has degree 1, degree 2 and degree 1, it is 3. It is degree 3, it is degree 3. Numerator is homogeneous of degree 3. This is also homogeneous of degree 3. So it is a homogeneous differential equation of degree 3rd, but of first order and first degree, because left side is dy by dx. If it is dy by dx or dx by dy, it is a first order and first degree. So how we proceed? We put here y is equal to vx, so that you will have dy by dx is equal to what? V plus x dv by dx. V is a function of x and y. Using in first, so first will imply, your first equation will imply now, it is v plus x dv by dx, v plus x dv by dx, it is your x square, y is vx, then this is x cube, this is v cube, yes, v cube x cube. This gives you v plus x dv by dx is, you can take x cube common, it is only v by 1 plus v cube. So that you can write x dv by dx is v by v cube plus 1 minus v. Now after this, let me come here. I am now here. It is my x dv by dx is equal to v minus v4 minus v by v cube plus 1. Okay, if this setup is not visible, I will write this setup also for your information. My setup is x dv by dx is equal to v by v cube plus 1 minus v by transposing v. So I am just trying to, is here variable separable, I can write it, yes, this is your v, v by v cube minus 1, this comes v4 minus v by, okay, this is your v cube plus 1 by minus v4 dv is equal to 1 by x dx. Yes, variables are separated. You could separate the variable. So integral is minus times integral of v cube plus 1 by v4 dv integral of 1 by x dx plus c. So you can write it integral of v cube, write this way, v cube by v4, because actually if it would be v4 here, then v cube here, we have to divide. It is known as improper fraction. It is improper way. Degree of numerator is 3, degree of numerator 3, denominator is 4. So we split here. Minus integral of 1 by v4 dv. You just see I am doing right or not. Yes, v cube minus v4 cut down. Okay, it is dv. This is your log x plus c. This is minus integral of 1 by v dv minus integral of v raised by minus 4 dv is log x plus c. You can write it minus log v, it is log v, it is minus v raised power minus 4 plus 1 by minus 4 plus 1, as you know it is log x plus c. You can write it minus log of, what is your v, y by x minus it is minus plus 1 by 3 v raised power minus 3 is equal to log x plus c. Now I will take this setup here. take it here. It is minus times log of y by x, then plus 1 by 3v cube is equal to log x plus c. You can write it minus log y minus log x. This is log of m by n, log m minus log n. This minus will go in, it is plus log x, plus 1 by 3 y by x cube is equal to log x plus c. Well, this is minus log y plus x cube by 3y cube is equal to c. So you can write solution is x cube by 3y cube minus log y is equal to c. This is the solution of this differential equation, which was a homogeneous, and we could not at the first setup separate here variables, but we have found that the differential equation is a first order and first degree and it's homogeneous. We put y is equal to vx and we have got the solution. Well, I will stop here, and next time I am coming again with some examples on this homogeneous differential equation. Then we shall go to homogeneous equations, differential equations which are reducible to homogeneous form. Some differential equations are such that they seem to be homogeneous, but there are some hurdles, and we have to remove those barriers, those hurdles, and we have to come that differential equation in the homogeneous form. Thank you very much. We will be meeting soon, very shortly, next lecture. That will be perhaps the 7th. Thank you very much. Wish you all the best.